The solar system appears serene, suspended in a featureless void, yet this calm is an illusion shaped by human perception rather than cosmic reality. In truth, nothing in the universe is still. The sun, along with every planet, moon, and fragment of dust bound to it, is moving relentlessly through the Milky Way. This motion is not gentle drifting, but a colossal journey, one that has been unfolding for millions of years without pause or intention. We live inside a system in motion, carried forward without sensation, without sound, and without any natural frame of reference to warn us that we are traveling at all. From the surface of Earth, the heavens appear fixed and eternal, yet that apparent stability masks a far more treacherous truth. To grasp this motion, it must be reduced to the scale of a human life. The solar system travels fast enough to cross entire continents in the span of a heartbeat, yet so smoothly that no biological sense can detect it. A person could live, age, and die beneath the same familiar constellations, never realizing that those stars are slowly shifting behind an invisible current. This velocity is not merely an astronomical curiosity. It is a form of exposure. Movement implies passage, and passage implies an environment through which we are moving. The question is no longer whether the solar system is traveling, but what it is traveling through, and whether that unseen medium is as empty or as harmless as it appears. We can only guess what conditions surround this path because the data offers no definitive answers. Scientists are struggling to understand how often our system encounters denser regions, or whether subtle changes have already shaped Earth's history. The danger is not immediate, nor is it dramatic, yet it is persistent. The solar system does not choose its destination. It simply continues forward, deeper into a vast, unseen environment that does not acknowledge our presence or our survival. In this quiet motion lies the paradox of safety and risk, a journey so smooth it feels like stillness, even as it carries us toward uncertainties we have barely begun to perceive. The universe remains indifferent to us. The local bubble surrounding the solar system is a region of space that appears deceptively calm, known as the local bubble. It is not a structure that can be seen with the eye, nor a boundary that can be touched, but a vast cavity carved into the interstellar medium long before humanity existed. This bubble was formed by ancient stellar explosions, supernovae that tore through surrounding space and swept matter aside, leaving behind a region of unusually thin gas. Within this cavity, stars drift in relative quiet, shielded from denser clouds beyond. Earth, the sun, and every planet have spent countless generations enclosed within this hollow, moving freely inside a cosmic shelter that feels permanent only because it outlasts human memory. The existence of the local bubble is not inferred through imagination, but through radiation that arrives from every direction. Soft X-rays permeate this region, produced when tenuous gas is heated to extreme temperatures by long-dead stars. Traces of radioactive elements, embedded in ocean sediments and polar ice, confirm that violent events once unfolded uncomfortably close to our system. Yet even with this evidence, the bubble remains poorly defined. Its edges are irregular, its density uneven, and its lifespan uncertain. We can only guess how stable this refuge truly is. The data offers no definitive answers about how long the solar system will remain inside it, or what conditions await beyond its boundary. What seems like a quiet neighborhood may simply be a temporary clearing, a pause between encounters with environments far less forgiving. It is possible that this bubble is already thinning, its walls eroded by pressure from surrounding interstellar clouds. Some models suggest the sun is drifting toward a denser region, where gas and dust accumulate in far greater quantities. If that transition occurs, the environment of the solar system would subtly but profoundly change. Radiation levels could rise, the heliosphere could compress, and Earth's protective systems would face stresses rarely experienced. These shifts would unfold slowly, over tens of thousands of years, unnoticed by civilizations that rise and fall within a single cosmic moment. Still, the uncertainty lingers. The local bubble feels like shelter, yet shelters can fail without warning. Its quiet presence reminds us that safety in space is temporary, conditional, and never guaranteed. Leaving the bubble, the solar system's long passage within the local bubble is not permanent, and evidence suggests we are already approaching its boundary. This frontier is not a clean edge, but a turbulent region where thin, heated gas gives way to denser interstellar material. There is no visible marker, no sudden line in space, only gradual change. As the sun advances, the environment around it thickens almost imperceptibly, altering pressures that act upon the invisible shields protecting every planet. To humans, this transition would feel like nothing at all. To the solar system, it represents a profound shift in the medium through which it moves. Beyond the bubble's edge, space becomes crowded in relative terms. Clouds of gas and dust, shaped by ancient stellar deaths, drift through the galaxy like submerged continents. Entering such a region would be similar to a vessel leaving calm water and slipping into a slow, unseen current. The heliosphere, a vast magnetic envelope generated by the sun, responds to these conditions by changing shape, compressing on one side while stretching on another. This distortion is not dramatic, yet it matters. It defines how much radiation penetrates inward and how effectively cosmic debris is deflected before reaching the inner worlds. Scientists can model these interactions, but they cannot observe them directly in real time. The distances involved are immense, and the changes unfold across spans far longer than a human lifetime. We can only guess how close the solar system truly is to denser territory, or whether it has already begun to cross that threshold. Some data hints at subtle shifts in interstellar particles entering the heliosphere, suggesting the surrounding environment is no longer as uniform as it once was. Still, the evidence remains incomplete, fragmented across decades of observation. If the boundary is crossed, there will be no announcement, no sudden darkness, no catastrophic signal. The transition would be quiet, measured in altered radiation levels and faint changes in magnetic pressure. Earth would continue to orbit, seasons would continue to pass, and life would remain unaware of the deeper journey underway. Yet the significance of such a crossing cannot be dismissed. It would mark the moment our system leaves a region shaped by ancient explosions and enters. The interstellar medium, interstellar space, is often imagined as empty, a perfect void separating stars, but this perception hides a far more complex reality. Beyond the local bubble, the solar system enters the interstellar medium, a thin but active mixture of gas, dust, and magnetic fields that fills the galaxy. Though sparse by earthly standards, this medium is anything but harmless. At high velocities, even the smallest particles carry immense energy. A grain of dust, no larger than smoke, can strike with the force of a projectile when encountered at cosmic speed. To a moving system, emptiness becomes a field of invisible hazards. This environment is shaped by forces that are difficult to visualize. Magnetic fields twist through space like submerged currents, guiding charged particles along paths that are anything but random. Radiation moves freely here, unfiltered by thick atmospheres or dense planetary shields. For worlds like Earth, survival depends on layers of protection that were never designed for prolonged exposure to such conditions. The interstellar medium is not hostile in a dramatic sense, but it is relentlessly unforgiving. It does not attack, it simply exists, indifferent to what passes through it. One of the most dangerous aspects of this region is its subtlety. There are no walls, no storms that can be seen forming in advance. Instead, danger arrives as a steady accumulation of impacts and radiation, each one insignificant on its own, yet profound when measured across millennia. Microscopic debris, accelerated by galactic motion, behaves like a constant spray of high-speed fragments. Over time, this can erode magnetic boundaries and alter the balance between a star and its surroundings. For the solar system, moving through this medium is unavoidable. The sun does not slow, and the galaxy offers no clear passage. We can only guess how dense the regions ahead may be, or how uneven their structure truly is. Scientists are struggling to understand how variations in this invisible environment influence planetary climates and biological stability. The data offers no definitive answers, only patterns that suggest cause without certainty. What appears tranquil from afar is, in reality, a vast expanse filled with quiet forces that test every system drifting through it. In this thin fog between stars, safety is never absolute. The sun's shield, the sun does not travel unprotected. Surrounding it is a vast magnetic domain known as the heliosphere, an invisible shield inflated by the solar wind and carried outward in all directions. This structure encloses every planet, extending far beyond the orbit of Pluto, forming a fragile cocoon between the solar system and the hostile interstellar medium. Within this boundary, charged particles from distant stars are slowed, deflected, or redirected, their paths bent by magnetic forces rather than allowed to strike freely. For life on Earth, this shield has been essential, quietly reducing radiation levels for millions of years without recognition or ceremony. Yet the heliosphere is not rigid. It responds constantly to pressure from the environment beyond it, expanding and contracting as conditions change. As the solar system moves into denser regions of interstellar space, That pressure increases, compressing the heliosphere on its leading edge. This compression reshapes the shield, narrowing the distance between Earth and the unfiltered radiation outside. The process is gradual, unfolding over thousands of years, but its consequences are cumulative. A thinner shield allows more high-energy particles to penetrate inward, subtly altering atmospheric chemistry and increasing biological stress. Measurements from distant probes suggest this deformation may already be underway. Instruments detect changes in particle flows and magnetic orientation that hint at an external force pushing back against the sun's domain. Scientists are struggling to determine whether these fluctuations are temporary or the early signs of a long-term transition. The data offers no definitive answers. Models disagree, and observations remain limited by distance and time. If the heliosphere were to compress significantly, Earth would not experience an immediate catastrophe. Instead, the effects would arrive quietly, as they often do in cosmic history. Increased radiation could weaken atmospheric defenses, influence cloud formation, and affect genetic stability over generations. These are not threats measured in days or years, but in epochs. Humanity, focused on the surface of its world, would likely notice nothing at all. The sun's shield gives the illusion of permanence, yet it exists only in balance with its surroundings. That balance is delicate. As the solar system continues forward, deeper into uncertain territory, the heliosphere must endure forces it has not encountered in human memory. The outcome remains unknown to us. Radiation and life, invisible energy constantly rains down upon the solar system, passing through space with little regard for planets, atmospheres, or living tissue. These cosmic rays are born in violent events far beyond our sun, accelerated by supernovae and distant stellar remnants to energies that defy everyday intuition. When they reach Earth, most are harmlessly deflected or absorbed, yet a fraction always slips through. On the surface, this exposure is minimal. At the level of the body, however, radiation becomes personal. Radiation is a quiet hazard. Each particle can damage cells, alter DNA, and seed errors that ripple through generations. Life persists not because radiation is absent, but because it is held to tolerable levels. That endurance depends on defenses that are thin on a cosmic scale. Earth's magnetosphere bends charged particles away. The atmosphere absorbs much of what remains, sacrificing itself molecule by molecule. Without them, the surface would be sterilized quickly. Even small increases matter mutation rates rise, climate and chemistry shift, ecosystems strain. Scientists are still trying to link past changes in cosmic exposure to evolution and extinction, but the record offers no definitive answers, only correlations buried in geology. And the radiation environment is not fixed. As the solar system moves through the galaxy, it passes through regions of different density. A denser interstellar cloud could compress the heliosphere, shrinking the sun's protective bubble and letting more cosmic rays reach the inner worlds. The effects wouldn't arrive as a single catastrophe. They would appear in statistics rather than sensations, in altered probabilities, slow biological pressure, subtle atmospheric changes. Earth itself preserves hints that this has happened before. Rare isotopes such as iron-60, created in supernovae, have been found in ocean crusts and polar deposits. They are timestamps of nearby stellar explosions that dusted the solar system with debris. Yet interpretation is hard. Erosion, tectonics, and time distort the signal, and tying cosmic events to specific biological stress remains speculative. What lies ahead is also uncertain. Astronomers see broad interstellar structures in the sun's path, but their shapes and densities are difficult to map from afar. Probes measure particles in fields, but only along narrow lines, leaving probabilities that shift with each new dataset. There will be no obvious warning from the ground. The transition, if it comes, will be gradual. That is what makes the threat unsettling, not speed, but patience. We plan for visible dangers while drifting through invisible ones. Earth is not anchored. It is carried, shielded by systems that respond to conditions we only partly understand. The journey continues regardless, and the most consequential changes may happen quietly, all around us, before we learn how to name them.